This single algorithm explains why GPUs beat CPUs by the orders of magnitude. Today, we will benchmark Prefix Sum, an algorithm also known as Scan, and on both GPU and CPU using real CUDA code, real measurements, and real throughput outputs. By the end of this video, you will understand how GPU parallelism actually works, not just it's faster. This video is part of my deep dive into CUDA optimization and AI systems engineering. Prefix Sum is not a toy problem. It's a foundational GPU primitive used in sorting, compaction, histogramming, and even ML pipelines. Now let's walk through the code step by step and see how GPU and CPU really compare. So what is Prefix Sum? So Prefix Sum is a symbol algorithm where each element becomes the sum of each and every elements before it in a particular array. Sometimes we can include that element or sometimes we exclude that element. When we exclude that element, then it is called exclusive sum. When we include that element, it is called inclusive sum. For example, here we can see that 3, 1, 7, 0, 4, 1, 6, 3 is the input array. Then the sum will be 0, 0 plus 3, 3, 3 plus 0 plus 3 plus 1, 4, like that. Here it is an exclusive sum.
So let's start with the CPU version of our code. This is our baseline, a simple sequential loop. As you can see, we are initializing the output as input 0. Then we are just adding up all the elements up to that input to the output. That's all that is happening here. And we are benchmarking this particular application or this particular piece of code using std chrono, and we are also calculating the memory throughput in GP per second, and this runs in O of n time in a single core. So moving on, when we have the CPU, here we are doing the CPU benchmark. Here we generate 1 million random integers and run the prefix sum and measure the execution time in microseconds. Then we compute the throughput, how many gigabytes of data we process per second. This gives us a fair baseline to compare against the GPU.
Now, why do GPU needs different algorithm? Now, here is the idea. You cannot parallelize prefix sum naively. If every thread updates its own element, they depend upon each other. That creates a racing condition. So instead, GPU uses a tree-based algorithm called Blelloch Scan, which has two phases, upward sweep and downward sweep.
So here we have our upsweep phase. So in the upsweep phase, as you can see, each kernel launch combines a pair of elements. And think of this like building a binary tree. It leaves at the bottom partial sums moving up. Every iteration doubles the stride, reducing the problem size in parallel. So here, as you can see, the stride doubles in every iteration. First, we combine the number. First, we combine neighbors, then groups of 4, then 8, then 16, so on. This is how reduce the elements into a single total sum in parallel. So that's why we have kept the stride as 2 here in the upsweep phase. Then we have the downsweep phase, the downsweep kernel that we have defined here. So the downsweep kernel is where the distribution of the sum happens. So the downsweep phase is where the prefix sum actually emerges. We work down the tree back, distributing the partial sum into the correct positions, which transforms the reduced tree into a fully exclusive prefix sum. And Blelloch algorithm usually generates the sum as exclusive sum, but right now we are trying to include the inclusive sum. So that's why we had to convert that particular algorithm into inclusive by adding the current elements to the output. So that's what we are doing here, making the exclusive algorithm as inclusive algorithm itself. So scrolling down to the GPU loop, here it is. So initially we check the data, we allocate memory, we copy the data from the host to the GPU. We run the upsweep kernels here, and we have the downsweep kernels here, and we convert them into the exclusive sum to the inclusive sum. So as you can see, each step is synchronized for the correctness of the output. Then we calculate the throughput on the time lapsed. You can check here. There is the GPU throughputs that we are calculating. Uh, GPU timing uses CUDA events, which gives the accurate kernel execution time. We measure the total GPU time in milliseconds, then convert it to GP per second for throughput. This is the most honest way to compare the CPU and the GPU as far as I know.
So in my machine, with millions of data, CPU is way slower than the GPU. Or otherwise, we can say that the GPU achieves multiple times higher memory throughput even with this implementation. And remember, this is not even the most optimized version of a GPU kernel. So why does GPU wins? GPU wins here because there is like hundreds of threads running in parallel. Memory access is coalesced, latency is hidden by wrap scheduling, and arithmetic intensity is really high. Prefix sum is a perfect demonstration of these strengths. But remember, it is not always that GPU will always win. GPU loses when the data is really small, kernel launch overhead is very high and it dominates the operation itself, and the memory transfer is also really high. This is why benchmarking is essential. Never assume is GPU is much faster than the CPU. So this prefix sum benchmark is more than an algorithm. It is a window to how GPUs work. If you understand this, you understand the foundation of GPU compiling or GPU computing. In the future videos, we will optimize this further using shared memory tiling, wrap primitives, and multi-block scans. Thanks for watching, and I will see you in the next deep dive video or my own experiments with new projects. Bye.